Hello, and welcome to this discussion of the idea of the black body. Now, the black body is a useful idealization that we're going to use as a starting point. The black body is a perfect emitter and absorber, so it absorbs all of the radiation that comes in contact with it. It has an absorptivity of 1. And at a given temperature and wavelength, no surface can emit more radiation. So the emissivity is always 0, regardless of angle, regardless of wavelength or anything like that. The other feature is that intensity is independent of direction. So it's what we call a diffuse emitter. It emits radiation equally in all directions. Now, it's the standard against which other surfaces are measured, but the reality is no surface is an actual black body. It's also important to note that, as in the diagram here, black body radiation exists in a cavity, a large substance with a small opening, regardless of what the surface looks like. The reason is because the radiation gets bounced around all over the place until it's essentially diffuse. And the emissivity behaves as if it was 1 because the radiation leaving every surface is equal to the emission plus the reflection from all the other surfaces. So cavities basically always behave as if they have black body radiation. Now, the spectral intensity of the black body is actually very well known. It follows the Planck distribution. It is continuous. Emission increases with temperature. So we can see that. As the temperature increases, we can see from the diagram here that a greater portion of that radiation occurs at shorter wavelengths or higher energy radiation. So you can see here that as the temperature increases, we get more radiation in these lower wavelength or higher energy regions. We should note here that the surface of the sun is about 5800 Kelvin, the highest temperature line on this chart, and it shows that the peak wavelength is right around green light. It's right in the visible light range. So this is why we can see visible light. Now, from the Planck distribution, we can get the Stefan-Boltzmann law by integrating the Planck distribution over wavelength. And so this is a very powerful analysis tool. And if the surface and the object and then the surroundings are both considered black bodies, we can then look at defining the net radiation heat flux as sigma t to the 4th minus alpha g, except alpha is 1 and g is sigma t surroundings to the 4th. So we have sigma t to the 4th minus sigma t surroundings to the 4th is the net radiation heat flux for a black body in a cavity or a black body within another black body. So the reality is that surfaces are not ideal. The black body is a useful idealization, but we have to account for reality. So real surfaces are going to have variations in the spectral intensity. They may not be diffuse. And the end result is the actual emission is very different from the Planck distribution. So we are going to define the emissivity of a material. And again, the emissivity of a material here is going to depend on wavelength, solid angle, and temperature. So this allows us to define the emission spectrum by relating a real material to our ideal black body. Generally, we don't need this level of detail for heat transfer problems. So what we're going to do is integrate emissivity over wavelength and angle and get kind of an average emissivity for the surface. So when we do that integral, we end up with something that depends only on temperature. It's important to recognize that this is a simplification. It's an engineering simplification that allows us to solve certain simple problems, and it is pretty reliable if we define the average emissivity properly. Now, we also assume diffuse emission for a black body, and in general, this is pretty reasonable. Now, no real surface is actually diffuse. However, if you look at the graph here, a non-conducting material has almost flat emissivity from the normal direction to 70-75 degree angles. So diffuse emission is pretty reasonable here. Emissivity is nearly constant with angle. A conducting material typically has a relatively small emissivity, and even though you can see it increases slightly as we go towards an angle of 90 degrees, Since it's smaller, the distribution can be considered flatter, and we can usually assume diffuse emission. It's not strictly true, it's an assumption we make, but it's a pretty reasonable assumption that allows us to solve engineering problems. So we typically use the normal emissivity, or the emissivity at 0 degrees, right here, to represent the emissivity of a surface. Now, typically, emissivity is low for conducting or metallic surfaces. These are surfaces that have a tendency to be shiny, reflective. And it's higher for non-conducting surfaces. If you have a highly polished metal surface, the emissivity can be as low as 0.02. This also means that oxidation can significantly affect the behavior of the surface. If you go from stainless steel, which is, one moment, this line, polished stainless steel, and then you rust the stainless steel, you end up oxidizing it, and you move to this line. So the emissivity changes quite a bit, not only in its magnitude, but in its trend when you oxidize a surface. So we change the surface from a conductor to a non-conductor, and we change its thermal properties. So when we're looking at designing engineering systems, we have to be very careful to either account for oxidation on the surface or make sure we try to reduce or eliminate oxidation on the surface to maintain the performance of our heat transfer system. We should also note here that for tungsten, if we see this line for tungsten at different wavelengths, the peak at different temperatures tends to be in the 0.3 to 1 micrometer range, typically between 0.4 and 0.6 micrometers. And this is the visible spectrum, and this is one of the reasons tungsten makes a very good filament for incandescent light bulbs. And then we can also look at total normal emissivity, the one we're going to use when solving most problems, as for different temperature or different materials at different temperatures. And you can see we have silicon carbide and stainless steel and tungsten and so on. And we can just get some general conclusions from here, and we can see the highly polished metals have very low emissivity, 0.02 to 0.07 or so, and metals typically have emissivities from 0.1 to 0.2, something like that. If they're not polished or not finished, they can be as high as 0.4, 0.6. Ceramics tend to have much higher emissivities, right? They're non-conducting materials. Graphites, minerals, glasses, and so on. And then we can get special finishes to get emissivities that are close to blackbody behavior, above 0.9 emissivity, but they're not quite there. So no real surface actually is a blackbody.